Law of conservation of energy. Energy can be transformed from one form of energy to another form of energy. In our day-to-day life, energy appears in different forms, such as solar energy, light energy, heat energy, chemical energy, wind energy, electrical energy, sound energy, muscular energy, mechanical energy, and so on. The sun is the ultimate source of energy that produces solar energy in the form of light and heat energy. Solar panels consist of a large number of solar cells and convert solar energy to the electrical energy. However, a solar water heater converts solar energy to heat energy. A plant also captures light energy from the sun to make food. Solar energy trapped by the plant enables them to change solar energy to chemical energy in the form of food. We also get wood from plants. Chemical energy stored in the form of wood can be transformed into heat and light energy. We know that the light energy enables us to see objects around us. A tube light is an example of light energy in which electrical energy is transformed to light energy. We also know that the heat energy causes an object to be hot. Heat energy can be produced by burning of fuels. Here, the chemical energy stored in fuels is transformed into heat energy. Some other sources of heat energy are the fossil fuels, such as coal and petroleum. They also store chemical energy. Chemicals in batteries or dry cells contain chemical energy. When a battery or a cell is connected to an electrical appliance, it transforms its chemical energy to electrical energy. Wind or moving air is also a source of energy. Windmills, when powered by the wind, produce energy. Windmills or wind turbines are connected to generators that convert mechanical energy of the wind to electrical energy. In a thermal power plant, coal is burned to produce heat energy which drives the electrical generator. In this way, heat energy is converted into electrical energy. This electrical energy can further be converted into heat energy or light energy. Sound energy is the energy generated by vibrations. Sound energy is not used for electrical power because the amount of energy that can be obtained from sound is quite small. But it is important to us as it enables us to communicate. Sound energy is also used to alert people, such as alarm of an ambulance. To lift a weightlifter uses muscular energy. However, the chemical energy trapped in our muscles is stored as muscular energy that enables us to do work. For opening a lid, we need mechanical energy. An object which possesses mechanical energy is able to do work. In the process of doing work, the object which is doing the work exchanges energy with the object upon which the work is done. When the work is done upon the object, that object gains energy, whereas the other object loses the energy. This gain or loss in energy by the objects is known as mechanical energy. In general, mechanical energy is the energy possessed by an object due to its motion, its position or its shape, such as when an object is in motion. It has kinetic energy that is also known as energy of motion. For example, a moving car or a flying bird. When an object is at some position, it has potential energy that is also known as energy of position. For example, water at the top of a waterfall or stored water in a dam. There are many forms of kinetic energy. For example, vibrational kinetic energy, rotational kinetic energy, and translational kinetic energy. Translational kinetic energy of a body of mass m moving with velocity v can be measured as half of mv square. If the kinetic energy increases, the object moves faster. The energy stored due to the vertical position is called gravitational potential energy, and the energy stored in elastic materials is called elastic potential energy. Gravitational potential energy of a body of mass m at a height of h from the ground is equal to mgh. The higher an object is from the ground, the bigger is its potential energy. Both potential energy and kinetic energy can be interconverted. For example, water is stored in a reservoir at a great height, possesses high potential energy. At the time of water supply, water rushes downwards with a great speed and easily reaches to the different parts of the city, and thereby potential energy is converted into kinetic energy. A body may have potential energy as well as kinetic energy at the same time, and the sum of potential energy and kinetic energy possessed by system remains constant at all times. The sum of both energies is called mechanical energy. A simple example of the transformation of kinetic energy into potential energy and of potential energy back into kinetic energy is a simple pendulum. When we give a push to the bob, it possesses kinetic energy, and as it reaches to its maximum height, its kinetic energy completely converts into potential energy. Energy of the swinging pendulum can be either potential or kinetic, or a mixture of potential and kinetic, but its total energy at any instant remains the same. Another example of such type of transformation of energy is the motion of a car on an inclined plane. When the car is at the peak of an inclined plane, it possesses only potential energy. When it moves downwards, its potential energy converts into kinetic energy. When the car moves on horizontal surface, it possesses kinetic energy only. Throughout its motion, there is a transformation of gravitational potential and kinetic energies, but again at any instant its total energy remains the same. In a dam, stored water possesses potential energy, and when the water falls, it attains kinetic energy. A water wheel is used for converting the energy of moving or falling water into rotational kinetic energy, and the rotating wheels help to produce electricity in the generators. Thus, energy of the running water passes from water to the wheels and ultimately gets converted into electricity. The water that turns the generator wheel loses energy and the generator wheel gains energy. The sum of the energies of the system remains constant. Here, in this activity, a brick is hanged at a height which possesses potential energy. For a hypothetical frictionless condition, when we drop the brick, its potential energy decreases to zero and kinetic energy increases to its maximum value, or in other words, its potential energy converts into kinetic energy. At every point, total energy remains the same. During the motion, the brick possesses both potential and kinetic energies. But if there is air, then some internal energy of the brick is also produced. In this condition, as we drop the brick, its potential energy decreases. Initially, its kinetic energy as well as internal energy increases, but finally its kinetic energy decreases and internal energy increases. In this case also, the total energy remains the same. This activity shows that energy can neither be created nor be destroyed. It can only be transformed from one form to another. This condition is referred to as law of conservation of energy. Let's relook the activity. Let the mass of the brick be m, and initially it is at height h. At that point, it has no kinetic energy, but it has potential energy equal to mgh, and thereby the total energy at point A comes out to be mgh. After falling a distance of x, it reaches point B, where it has kinetic energy equal to half mv square and potential energy equal to mg multiplied by h minus x. Using the second equation of motion, the velocity of the brick at point B comes out to be under root 2gx, and thereby the total energy at point B also comes out to be mgh. Similarly, at the ground, its total energy again comes out as mgh. This shows that it is clear that potential energy of the body continuously decreases as the body falls, whereas its kinetic energy continuously increases as it comes closer to the ground. That is, potential energy is transformed into kinetic energy. Similarly, if we throw a ball in an upward direction, kinetic energy of the body continuously decreases and its potential energy continuously increases. That is, its kinetic energy is transformed into potential energy. Here also, total energy of the ball remains constant throughout the motion. Let's see an example. A rocket of mass 2.5 multiplied by 10 to power 6 kilogram takes off from a launching pad and acquires a vertical velocity of 1 kilometer per second at an altitude of 30 kilometers. Calculate the total energy of the rocket. First of all, let us convert all the values in SI units. Kinetic energy of the rocket at the altitude of 30 kilometers comes out as 1.25 multiplied by 10 to the power of 12 joules. And the potential energy comes out as 0.75 into 10 to the power 12 joules. Therefore, the total energy, that is the sum of kinetic and potential energy, comes out to be 2 multiplied by 10 to the power 12 joules. Let's see another example in which a ball dropped from a height h. When it reaches the ground, its velocity is 50 meters per second. Let's calculate the height h. When the ball reaches the ground, the potential energy of the ball is converted into kinetic energy. By equating the two energies, the initial height of the ball comes out as 125 meters. Rate of doing work. Whenever a force acts on an object and the object is displaced, work is said to be done on it. For example, when we push a cart, we do work. It can be noticed that greater the displacement, greater is the work done. Similarly, greater the force, greater is the work done. This shows that the work done depends upon the amount of force and the amount of displacement. Hence, work done is the product of force and displacement when a force is in direction of displacement. If two or more forces are acting on an object, then the net work done on the object is the algebraic sum of the work done by each force separately. For example, when a cart is forced to move on a rough surface, the friction opposes the motion. That is, the friction and the displacement are in opposite direction, and thereby the friction force does the negative work on the cart. And the net work done on the cart is the algebraic sum of the work done by each force, that is, the applied force and the friction force separately. If the applied force and the opposing force, that is, frictional force, are equal, the net work done is zero. Further, when the force is applied at an angle to the displacement, then the work done is the product of the component of the force in the direction of displacement and the displacement itself. It can be noticed that if the applied force and the displacement are perpendicular to each other, the work done becomes zero. So, work has nothing to do with the amount of time during which the force acts to cause the displacement of the object. Sometimes the work is done very quickly and other times rather slowly. For example, a rock climber takes unusually long time to elevate his body up a few meters along the side of a cliff. On the other hand, a trail hiker might elevate his body to the same height in a short amount of time. Both the people might have done the same amount of work, though the hiker does the work in considerably less time than the rock climber. The quantity that has to deal with the amount of time during which the force acts to cause the displacement of the object is known as power. In other words, it is a measure of the speed with which work is done on a body. Thereby, power is the rate at which a certain amount of work is done. Hence, the hiker has a greater power than the rock climber. Here, one can see two lifts rising up in two multi-storied buildings separately. One is faster than the other. However, both the lifts are doing the same amount of work. The faster lift is said to have more power than the slower one. Power of an object is calculated by finding the ratio of work done by an object to the amount of time taken to do the work. For an object in linear motion, the change in the kinetic energy of an object is equal to the net work done on the object. Similarly, if an object is raised to a height, the change in its potential energy is equal to the amount of work done on the object. Whereas, if the object is allowed to fall from a height, the change in its potential energy is equal to the amount of work done by the object. In other words, the energy spent or consumed by an object is the capacity of the object to do work. Thereby, the energy spent or consumed per unit time is called power. For example, when a boy climbs an inclined road, he would be more tired while running instead of walking. Here, the change in energy to overcome the gravitational force, that is, his potential energy, is the same, but the rate at which the energy is transformed or the work is done is different. It is clear that lesser the time, more is the power. In general, power is the rate of doing work, and the power is required to produce a constant speed against an opposing force such as gravitation or friction. Therefore, it can also be measured as the product of the applied force and the velocity. Similar to work, power is a scalar quantity, and its SI unit is watt, named after the British engineer James Watt, who developed the first steam engine. An object is said to have a power of 1 watt if it can perform 1 joule of work in 1 second. Other units of power are milliwatt, kilowatt, megawatt, etc. 1 milliwatt, which is 1,000th of 1 watt. 1 kilowatt, that is equal to 1,000 watts. 1 megawatt, which is equal to 1 million watts. Whereas in the British system, the unit of power is horsepower, which is equivalent to 746 watts. It was James Watt who compared the output of a steam engine with the power of draft horses. The story behind this is that James Watt was working with ponies lifting coal at a coal mine. He was interested to measure the power available from one of these animals. He found out that on an average, a pony could do 22,000 foot-pounds of work in a minute. He also estimated that a horse could do 50% more work than a pony. In this way, he estimated the measurement of horsepower as 33,000 foot-pounds of work in 1 minute. That is equal to 550 foot-pound per second. In MKS system, it comes out to be 746 watt. For more understanding the concept of power, let's try some problems. In the given problem, measure the power of a kitchen blender if it can perform 3,960 joules of work in 20 seconds. Here, quantity of work done and the consumed time are given. Therefore, by using the relation for power, it can be measured as 198 watts. In this problem, a man pulls a bucket of water of mass 15 kg from a well which is 20 meter deep in 25 seconds. Let's calculate the power used by the man. Here, mass of the bucket is 15 kg and the depth of the well is 20 meter. In pulling the bucket of water, the work done by the man is stored as the change in its potential energy, which is equal to 3000 joules. Since this amount of work has been done by the man in 25 seconds, therefore power used by the man comes out to be 120 watts. Let's see another problem in which a man having mass 60 kg climbs up 60 steps of stairs in 2 minutes. If each step is 25 cm high, measure the power used in climbing the stairs. Height of one step is given as 25 centimeters. Therefore, the total height covered in climbing the stairs of 60 steps is 15 meters. Since the work done by the man in climbing the stairs is against the gravity, therefore the potential energy is used, which comes out to be 8,820 joules. Further, the time taken in climbing the stairs is 2 minutes, that is 120 seconds. Hence, the power comes out to be 73.5 watts. Let's try another problem. Calculate the power of a water pump which takes 60 seconds to raise 240 kg of water to water tank placed at a height of 25 meters. Since pumping the water from the ground level to some height is the work done in carrying the same mass to the given height and hence equivalent to rise in the potential energy, which comes out to be 58,800 joules. Since the time taken by the water pump is 60 seconds, therefore the power of the water pump is 980 watts. Let's see one more problem. In a bullock cart, the bull exerts a pull on a cart of 600 Newton, so that the bullock cart moves with a constant speed of 72 kilometers per hour. Calculate the power developed by the bull and also find its equivalent in horsepower. Here, the force exerted by the bull and the speed of the bull were given as 600 Newton and 72 kilometers per hour respectively. First of all, convert all the given quantities in the same unit. Since power can also be measured as the product of the applied force and the speed, therefore, the power exerted by the bull comes out to be 12 kilowatt. Further, 1 horsepower is equal to 746 watt. So, the power of the bull is equivalent to 16.09 horsepower. While moving a load against the frictional force, some of the energy is converted into heat, some into sound, and the rest of the energy moves the load. The heat or the sound energy is lost to the surroundings. That is, whenever energy of a device is used to do the work, some of that energy is always lost, and the percentage of the energy that is transformed to a useful or desired form of energy is called the efficiency of that device. More is the efficiency of a device, less is the wastage of the energy. In a water pump, energy is supplied by the pump is utilized in pumping up the water, and some energy is wasted due to the friction of the pipe. That is why when we touch the water pipe during the pumping of water, it appears to be hot.